In this video, you'll learn how to verify concrete for compression. Now, I know what you're thinking. Why should I verify concrete for compression? It has really good compressive strengths. And yes, you're right. Usually we just add reinforcement because concrete is very weak in tension. But there are, however, some design situations where concrete also has to be checked for its compression capacity. And in this video I'll show you 3 examples where the compression verification might be critical, and I walk you through the 5 steps of how to verify concrete compression. But before getting into, I want to welcome you to episode 3 of the Reinforced Concrete series, where I teach you everything you need to know about reinforced concrete. My name is Laurin. I'm a full-time structural engineer, and in the next weeks and months I'll teach you how to design and verify reinforced concrete on this channel. So if you don't want to miss any of the future videos and episodes, then subscribe to the channel. And now let's get into the topic of today. Let's start by looking at the step-by-step process of verifying concrete for compression. And these are the steps I always follow as a structural engineer. So step 1 is defining the characteristic concrete strength. This means, are we using C25, C30 or C35? Then finding the partial safety factors, gamma. Step 3 is calculation of the design compression strength, FCD. Step 4 is the calculation of the reduction factor. We only need this for the compression strength of struts with ties. And the last step, step 5, verification of compression. Alright, let's look at 3 examples where compression needs to be checked. When you start out as a graduate structural engineer, compressive concrete failure are usually not something you think of, because concrete is great in compression, right? There isn't even a section for compression verification in Eurocode, just about struts. But let's run through 3 examples where concrete compression was critical in the projects that I've worked on. So, example 1. Column supporting a continuous wall. Reinforced concrete columns have a relatively big capacity for vertical loads compared to their cross-section. And usually we verify columns with a software or with like an Excel sheet for its vertical and horizontal loads with an MN diagram. So the software tools or the Excel tools are usually based on MN diagrams. Then if the column doesn't verify for these loads, we just add reinforcement. But we often forget the compression verification. The problem here is that for concrete compression, we can't just add reinforcement. Either the compressive strength of the concrete or the cross-sectional area needs to be increased. And this can result in additional costs and a lot more CO2 that we emit through using a C35 instead of a C30 concrete. So from my experience, the concrete compression strength becomes critical for the center column here, because we have a continuous beam or a continuous wall, because we have a relatively small cross-sectional area of the support. When you think of a cross-section here, then usually precast concrete walls, they might often be 0.2 meters. And then maybe the column is a bit thicker, like maybe 40 centimeters, 0.4 meters. But since the wall is only 0.2 meters, we can only transfer the compression in those 0.2 meters. So we can't really use the full width of the column. Now let's look at example 2, struts of moment stiff corners of frames. So frames can be used to stabilize a building or to take up vertical loads. These horizontal and vertical loads then lead to bending moments in the corners, like this bending moment and this bending moment. But the bending moments can actually, it depends on the load, they can also act in the opposite direction. One method to design and verify moment stiff concrete corners for the bending moment is with a strut and tie method. In a future episode, we'll also dive deeper into what the strut and tie method is. But basically, this method splits the structure into struts, which are compression members, and then ties, which are tension members. The axial forces of the struts are taken up by the compressive strength, of the concrete, tension forces by the ties, which are reinforcement. So where we define ties, we have to add reinforcement. And now this bending moment from the picture above, which we also visualize here, can now be split into a compression and a tension force. Because, yeah, if we have a moment, we can split that up into a pair force. The strut and the tie equal the moment divided by the distance A. And we can see them here and here. And because we have a moment and force equilibrium in this corner, we also have a tie here in the opposite direction and a strut here, because we have the same moment on the other side of the corner. Now the reinforcement will then be verified for the tensile force T, so this one, and the concrete force C. But what's even more critical is actually transferring the tensile force T to the diagonal strut. And this is something I have seen many people forget in their design calculations, because we have this node here, and we can only transfer this tensile force down here to this tensile force if we have a diagonal normal force, which is compression in our case. And somehow when we pull from here and here, we get this compression diagonally, and somehow we have to transfer like our tensile forces to the compression. And one way of doing it is to use the area of the bending radius of the reinforcement, which you can see here. But as you can imagine, like a rebar is like this thick maybe. You don't have a lot of area where you can actually transfer all the tension forces to the concrete. And the smaller the area, the bigger the compressive stress C. And yeah, subscribe to the channel. I will show exactly this example in a future video, how you verify those corners. Now, example 3, joints of precast concrete buildings resisting loads from shear walls. So the vertical loads from precast concrete walls travel through the joint. So you have a vertical load here, and they travel through the joint here. Because in precast concrete buildings, you usually have slabs that are hollow core slabs, and you usually don't apply any vertical loads here on the slabs, because you know they are kind of some parts of the cross section are hollow. So again, you reduce the area where you can transfer the vertical load by a lot. And this becomes even more critical if the wall is a shear wall, because then in this case the vertical load is concentrated on an even smaller area, because of this horizontal load, all of this vertical load is kind of traveling down here in this compression zone. Alright, now let's run through the 5 steps to verify compression of reinforced concrete. Step 1, define the characteristic concrete strength, FCK. As a first step, we need to define the concrete strength, and we find the concrete strength classes in Eurocode table 3.1. And for this video tutorial, we'll use a concrete class of C30, which has a compression strength of 30 megapascal. Let's move on to step 2, find the partial safety factors gamma C. From table 2.1n in Eurocode 2, we will find the partial safety factor from concrete as 1.5. But note that these factors can be different in other countries. For example, in Denmark, you even have different partial safety factors depending on the structural type of the building. So if it's precast elements, you have a lower partial safety factor, and if you have in situ concrete structures, you have a higher partial safety factor. Now, moving on to step 3, calculate the design compression strength. We calculate design concrete strength by dividing FCK through the partial safety factor and get 20 megapascal. Now, for examples 1 and 3, this is the design compression strength that needs to be greater than the design compression stress from the loading, which we'll show later on. And according to Eurocode 2, FCD can be used as the compressive strength if there is a transverse compressive stress, like in this example here, or if there's no tension force, like in this example. But for example 2, for the struts, the strut and tie model, where we have, struts and then maybe we have one tie, we have to further reduce the design resistance of the compressive strength. Therefore, we have to calculate a reduction factor in step 4. And again, this only applies if you calculate the compression strength for nodes with struts and ties. So according to Eurocode, the reduction factor is calculated in our case for a C30 as 0.88. And with another formula from Eurocode 2, we can now calculate the design compression resistance of struts with ties. And this is 10.56 megapascal. And if you just compare it to FCD, it's like half. So you see how much the design resistance is actually reduced if we have ties. But again, this formula can even be defined differently in Euro National Annex. So check that up. Now the final step, step 5, the verification of compression. In this last step, we'll verify that the compression stresses from loads are smaller than the compression strength. Let's use example 3 with a line load of 400 kilonewton per meter and an effective width of the joint of 50 millimeters, which you can see in this picture. And here you can see the joint width and the compression stress. So first we calculate the stress, sigma C, as 8 megapascal. So we divide the line load, 400 kilonewton per meter, by the joint width, which is 50 millimeter. Now we can calculate the utilization ratio, and we can see the utilization ratio is 40%. Also note, in this case, we don't have transverse tension, we just have compression. So therefore we can use FCD as the compression resistance. Now, final words. As I said in the intro, I've seen a few projects where this compression verification has been forgotten. I hope after this video you won't forget compression verification in your projects. And if you don't want to miss any new structural design tutorials, then subscribe to our free weekly newsletter. Link will be in the description below. Let's design better structure, and I see you in the next one.